All right, and we're back. And ladies and gentlemen, our next speaker of the evening is Denis Grey with Occultations Then and Now. Dennis.
Thank you very much, Tom. And thank you, everybody who's here in person. We've got a good group here tonight and a few familiar faces and a few new faces. So it's great to see everybody. So I've titled my talk Occultations Then and Now as a way of sort of contrasting kind of the way things were 25 or 30 years ago in this particular branch of astronomy with the way they are now. And to try and share with you kind of my excitement on how things have developed very quickly and very organically, as a lot of volunteer people have put a lot of time and energy into making what I consider to be a completely foolproof occultation recording and monitoring system, which is available today. So I'm looking forward to sharing a little bit of this story with you. Before we get into it, though, I think for the benefit of people who may not be familiar, I'll just do a little digression into what are occultations and why do we care about them. We'll talk about how we used to do occultations back in the good old days, and we'll talk about how we're doing it now. We'll highlight some of the new collaboration tools and the new hardware and software tools that are very exciting. And we'll talk about sort of the future of occultations as we go forward. All right. So the first thing is, what is an occultation? And so essentially, it's an event which makes this an event-based astronomy, which is kind of cool. And it occurs when one thing passes in front of another, partially or totally blocking its light, often causing it to visually disappear completely. Right. So that's the cool thing that we see, and you can usually only see it from a specific spot on the Earth, and that's it. So, can anyone name for me one kind of occultation that you may have been lucky enough to go to see recently? Yes, sir, in the back. A total solar eclipse. That's exactly the answer. So, if you think about it, a solar eclipse is when the moon goes in front of a bright object, the sun, and blocks it out. And if you're not standing on the right spot on the Earth, you won't see anything or anything very interesting at all. But if you're in exactly the right spot, you can see it get entirely out of the way that way. So, when we're working with occultations like that, astronomers working together can use the combination of information that can be recorded. So we're interested in, when did the star get blocked out by the thing? When did it come back when the thing moved out of the way? And where exactly were you on the Earth when you saw it disappear and reappear, right? So that information, with some math and calculations and a little bit of everything, can be used to actually determine the object's pretty precise shape and size. So this is a profile here of an occultation that happened in 19 I think it was 2001, of the asteroid 90 Antiope. So this was shown to be a binary asteroid. So we weren't sure about the binary nature of this asteroid. We kind of had some measurements that its light curve kept going back and forth in a cyclical manner. But this not only showed us exactly how close they were, we got a sense that one of those asteroids has got a funny shape. And because we now know the size and the distance between them, we can determine their mass and their density and all kinds of other cool stuff about it. So when you think about it in terms of how this looks on the Earth, right? So the geometry is that we've got a bunch of people A, B, C, D, and E, all scattered in different locations, but they all have in common is that they're standing in the right spot to be hit by that shadow as it comes across the Earth. And that shadow can cross the entire Earth in about 5 minutes, 10 minutes, half an hour, depends on how fast the asteroid is going, how far away it is, and so on, right? And so what the observers see is, observer A sees nothing. It missed him or her because he's outside of the shadow path. See, he's up in Edmonton there where the Oilers are. So, but B, C, and D, they see they see that asteroid getting away, and E also misses it. He's down there. So taking B, C, and D together, we get an information about the size of the asteroid, and A and E give us constrain how big it can absolutely be. So that information all put together, it gives us this information, or gives us all of this cool stuff that we find out about the asteroid. And what we're doing when we're looking at these timings is we're looking for a light signature or a light curve signature that shows us exactly when it goes out and when it comes back, right? So if we're trundling along here, it's a certain amount of time, we've got a certain amount of time. All of a sudden, one of our stars, the blue star in this display, goes gone, and it hits all near zero, and then time passes, poof, comes back, right? So that's telling us the disappearance and the reappearance time. So that's a view of my individual data. So if we think back on that, those chords, I could be B or C or D. This is what I'm seeing when I look at my data, when I review my video recording or whatever. This is what I'm seeing. I'm seeing an out and I'm seeing a back, and that precise timing there gives us that information. Now, of course, the location is very important. You need to know where you are in the earth. You can't just sort of say, well, I was wandering around somewhere in North Dakota and I think I saw this thing. That's not really very helpful. And so, in order to get everyone working together, a big part of this process is to have predictions. So, you need to know where to go. Where is this going to happen? What star are you supposed to be observing? There's an awful lot of them out there to choose from. And when exactly is this event likely to happen? So that's that. And then, of course, the other, of question of the four W's is, why did I forget to bring my power supply when I went out on this adventure? So that's another question, but that's an existential question for all people that are interested in this hobby. So that the more important why, not just where is my power supply, but this is another example of what Andy was just talking about, which is citizen science. So occultations are really useful in the world of science because they constrain that size of the occulted body. So we know roughly how big that is, and we can confirm both double stars and asteroid satellites with this. So if the asteroid passes in front of a double star, you'll see half of the light go out and then the other half of the light go out, and then half of the light will come back and half of the other half of the light will come back. It's a very, very visible signature on that light curve, which goes, wow, I've discovered or confirmed a double star. That's pretty cool. Same thing can happen with the asteroid. So if it's a double asteroid like Antiope there that we showed you the example, people that are far away from some other people will see an occultation at a different time. It'll be a different asteroid, so it'll have a different duration. We put all that information together, we've discovered a double asteroid. And also very important and kind of important, for defense and so forth of the Earth, constraining the size of the orbital parameters and getting them more accurate. So if you predict an occultation and you think it's going to happen at this time and it happens 3 seconds earlier, well, that means your prediction was pretty good, but why the 3-second difference? That's a change in the orbital characteristics of that asteroid, which might mean maybe it's had an encounter with some object, something slowed it down. Maybe our astrometry wasn't very good in the first place, and so forth. So that's a little bit about the why, or the what is an occultation. I hope that's clear to everybody. That makes sense. Getting a few nods. Good. All right. So how did this happen in the past? So first of all, location. Well, location didn't used to be as easy as it is now. So essentially, you'd start with a topographical map and you would see where certain highway met certain other highway, and you'd try to remember where you drove out to, and you kind of do X marks the spot, and then you would go on the map and try to figure out the latitude and the longitude and all that stuff. So you could do it and it would work, but you were never going to be that precise. So you were going to be, probably plus or minus half a kilometer, quarter kilometer, something like that. It was going to be a little messy. And then in terms of observing this, we were using our Mark I eyeballs mostly. This was kind of before video cameras were very popular. They were very expensive. So people were doing a lot of this with their just looking through the eyepiece, which meant that you had to keep looking and don't blink, because it could just happen when you're blinking. So you have to keep looking at it and keeping looking at it until it happens or doesn't happen. So anyway, that was always fun. And then timing. The most reliable source of timing was shortwave radio. So there were time signals that would come, and you would basically have a time signal that would go boop in the top of the hour, and it would go beep, 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 and you'd have that regular time signal. You'd synchronize your chronometers, and you'd know that 8 o'clock was the most recent beep. And so you'd count how many boops you had. So you could say, well, it happened at 29 and a half seconds after 8 o'clock, and it unhappened at about 33 and a half seconds after 8 o'clock. And it was all a bit of uh, a, a process of making sure that you kind of estimated that and recorded it. And then what are you recording exactly is your own visual impression of what happened. So what would happen is people would be looking at the eyepiece, you'd have a tape recorder going, you'd have a shortwave radio going, you'd be looking at the eyepiece, you'd yell out, and then you go back, and that would be your recording. And then you'd say, yes, I saw it, and you'd be really happy about it. But then you'd have to go back on that tape recording and go back and forth and try to get that timing just right. So this was also, again, a source of potential error, particularly because everyone has a personal equation. How many people here know their personal equation? One person. Very good. Well, that's actually more than I thought. So a personal equation was essentially your estimate of your reaction time, because nobody's reaction is perfect. So you see this thing go out, and it's all very exciting. And then people go, oh, out, right? And it's like, well, that kind of thing is going to put you off by half a second, 3/4 of a second. And the timing is very important. So you're trying to get it as accurate as possible. And so there were actually rehearsal things you could do and practice on to determine what your average delay between the time you saw something and the time you yelled about it was. And everyone would say, well, my personal equation is 0.2 seconds or 0.25 seconds or something like that. So this was all part of it. All right. So you would rehearse and you would estimate and you would try to figure all of that out. So all of these things basically added up to a lot of sources of error: the map locations, the timing, the recordings. The other limitation was predictions. So we have to know when to look at what in order to see anything, right? So one limitation there was the accuracy of star catalogs. So star catalogs have improved enormously in the past 20, 25 years. We used to have the Tycho catalog, which would kind of tell you the star is kind of around here somewhere, over roughly there. And then you'd say, well, the asteroid's going to be in the neighborhood. So then the chances of this star over here actually meeting that asteroid over there would be hard to manage. Now we can constrain that messy area where we think the star is right down to a very, very small area. It's much more accurate. Similarly, asteroids are much more accurately known now. So we're able to get much better accuracy on our predictions, and a lot more predictions. We're able to find more events. And back in the day, only very large asteroids like Ceres and Vesta could really be tracked well, because they would be big enough to cover the star kind of no matter what. So, essentially the bottom line here is that we would end up with lots of, error bars. So scientifically, yeah, we know something happened. We know approximately when it happened, and we know approximately how big it was. All of these approximations would add on top of each other, and in the end, you'd end up with something. The good news is, like, some information is better than no information, right? So that's how science moves forward. We gather what we can with what we've got, and then we look at the problem. We say, well, gee, we could do better. And yes, we can do much better nowadays. So let's talk about occultations now. So one of the most important things has been communication. So the internet has, of course, allowed for enormous amounts of collaboration and data sharing. And occultation feeds now are being generated by various astronomical data sources, observatories, and observing programs that are pulled together and give you probabilities, expected durations, magnitude drop that you can expect to see, what the star map is exactly, and where to find the target star and everything. And interested observers are able to participate through Occult Watcher software, which I'll show you in a minute. In terms of recording, now we have astronomical video cameras. They've got high sensitivity. The frame rates are pretty predictable, and we're able now to precisely, as I kind of showed on that other picture with the drop in the star's light output, precisely identify the when of the outs and the ins for the occultation, down to the limit of whatever that camera system is. And when you're looking at occultations, it's a system combination. It's the camera plus the telescope. So the bigger the telescope, the deeper you can go with to find stars. The smaller the telescope, the shallower you're going to go. And of course, one of the other things about having a recording is that you can actually confirm with confidence that you were actually looking at the right star. Now, I'm not mentioning any names, but it is possible that some astronomers that I know personally have spent a whole night watching the wrong star to see if it disappeared and were unsuccessful at their occultation. I'm not naming any names. But anyway, we'll carry on. And then the other thing that's nice about this is that visually you needed a really distinct drop in brightness in order to really know that you saw the thing, right? But photographically or video wise, you can see a subtle change in that. So the example is, I have an asteroid at 9th magnitude. I have a star at 9.2 magnitude. So when that asteroid gets in the way there, I'm going to lose 10 or 15% of the light output. Probably not enough to notice visually, but on a camera, I can see that drop off. I can see I'm still seeing the asteroid, because sometimes the asteroids can be bright. Sometimes they're dim little things at 14th or 15th magnitude. And basically you don't see the asteroid at all. You just see the star disappear. But sometimes they can be very close. And that's where the recording technology comes in and really helps. Of course, location, well, all of that map work and all of that details, that's gone out the window now. GPS tells us down to within 20 feet, 10 feet, exactly where we were standing when the occultation happened. And also the timing of GPS allows us to be down to a fraction of a second. So you can have a GPS not only tells you where you are, but it also tells you exactly when you are. And so you put that information together, you connect that GPS to the video, and a lot of times what we have there is essentially a video overlay where we put the timestamp on each frame that's coming out of the camera. So when that frame shows us that that light drop has happened, we can read it right off the screen. Oh, that happened at 10:52, 49.21 p.m., right? And that becomes part of our data reporting there. And so there's two versions of this. One is sort of an analog camera where we're overlaying the timestamp. And then you can also get digital cameras which actually directly insert it, but they're functionally the same, right? And then the other thing, of course, is the collaboration piece. So the software that we've been using for most of my adventure with occultation is called Occult Watcher. So it's Windows only software, so that's limited some people who are Windows challenged. There are some of them out there, but it has over 2,500 collaborators around the world. And essentially the process is you enter your sites, and you say, here's where I might want to go to observe occultations. You can get a set of predictions for that location, and you review the ones that you want. And if you think you've got one that makes sense for you, and I'm usually looking for something that's not too early in the morning, it's got a reasonably bright star, it's got to be kind of 30 degrees up or more, because I live downtown and I need at least 30 degrees to get over all the muck. I can register for that event and tell everyone in the world that I am registered for it. So if we take a look at that, where is it? Hello. It disappeared on me. Don't do that. There we go. So this is Occult Watcher, the software here. And you can see here that I've registered for, whoops, wrong. Stop that. Thank you. Must stop presentation. End slideshow. There we go. Okay. Sorry about that. There we go. Now we can see it. Okay. It's a little hard to see, but I'll see. I can't embiggen this anymore. But essentially what we're seeing here is a list of events with various things about it. Probability of the event is interesting. So a high probability means that there's definitely going to be something. And here is an example of an old asteroid 640, Brambalea. And you can see here in the bottom, this is the projected shadow path. It's the blue is the high quality projection, and it's got a little bit of pink around it, which means that's the uncertainty. So we really know a lot about this asteroid. We know its size. We know almost exactly where it's going to be. And my location is right here, this black spot. So I can see how other observers are set up. So we've got Drago over here, and we've got myself over there. So two people have signed up for this occultation, which is going to happen at 4:51 up to 3 seconds. It's going to be a significant drop in magnitude in the constellation Aquarius, southeast 31 degrees. So this is a good one, and it's expected this weekend on Sunday, May 11th. We have another one, which is a very different kind of occultation here. Here we've got an asteroid number 397,718. That is a very recently discovered asteroid found in 2008, and it's a small space rock. And so you see here with the pink at the bottom there, it's got a lot more uncertainty. We don't really know for sure where this one is. We think it's going to be here in the middle, but it really could be anywhere in this pink zone, right? So unlike our big asteroid 640, this one is a real mystery box. And if I were to go ahead and try and see it, my estimated probability of seeing it from my location is about 3.2%. If I do see it, though, we would nail exactly where that asteroid is and significantly constrain its orbit characteristics and so forth. So it's kind of useful, but you get a lot of this information here. And what the cool part of this, of course, is the collaboration. So I'm registered here, and on the observation planner, there's 2,513 users, 1,000 events that have been coordinated, 9,000 stations, all of whom, to one degree or another, are participating in this process. And if they get a hit, you submit it to the central clearinghouse. And if they find out something interesting about your asteroid, your name will be included on the paper that goes with that interesting asteroid. So this tool has been in use for about 15 years, and this is what I would almost call, it's still very useful now, but it's not necessarily the state of the art. Am I seeing again? Okay, hang on a sec. And I want to go to, we'll get there fast. I know there's a get there fast button, but we'll just go ahead. All right. So we just had a quick look at Occult Watcher. So now there's a new and improved version called OW Cloud. So this is a cloud-based application which is also come from our friend Hristo Pavlov. And this man, I believe he lives in the Philippines and Southeast Asia somewhere. He is just making this amazing software just for fun and profit and to help people out. There is no profit in it, I should say. But essentially, this is consolidating all of the predictions, and it includes a built-in search tool to help you find occultation opportunities. And it gives you all kinds of interesting information. So if we compare what I just showed you with Occult Watcher here, so this is essentially the search feature. And again, I got to stop the presentation. Yes, thank you. All right. Stop the slideshow. There we go. All right, back to my browser. There we are. So, so I have my own login, and this login is actually connected to Occult Watcher. And if I go to the search here, I can basically have a set of filters where I have my favorite locations here. So I've got the Car Observatory, I've got the Carswell Observatory, which is the observatory right up here, and I've got my own home included as locations. And what I can do here is I can pick a date, I can pick how far ahead to search, and I can go and look for occultation opportunities that might be there. And I can see here we've got some interesting ones. So there's the Brambilla one that we were just talking about. And I can see that Brambilla is going to go over this observatory as well. And I get a lot of useful information. So it's a 10th magnitude star, so that's pretty reachable by a small telescope. 4.2 magnitude drop, it should disappear up to 3 seconds, 100% probability. And I can go in here and I can look at the location here, and I can zoom right in, and I can see exactly what the predicted path is over the city of Toronto. So I can actually go straight in here and I can go more depth, and I can, oops, that's the wrong plus button. Thank you. So here I can see, I can actually go on here and I can mark, I can go right down to the Carswell Observatory and I could mark my location as a participant for that location. So anyone here who has a telescope and is interested in trying this out can go on this website, set up a little search profile for your favorite location, and see if you've got any occultations coming up soon. It's much easier than working with Occult Watcher, but it's all driven off of the same database and the same capabilities that are there. And then once you pick your option here, so let's take a look at this Brambilla one here. You can now go into events and look at a specific event. And you can drill right in. Oops, so let's go and find Brambilla here. All right, search. Should be there. Okay, it's a little flaky for some reason. Come on. All right, I'm going to go at this. I know there's another way to get here, but I'm having trouble executing it. So what I'm going to do here is I'm going to go through the other path, which is to use the old software and view details on the web. So I've got the option here to go view details on the web, which should take me right there. And there it is. Okay, so I have all the information now about this occultation of Brambilla. And here you can see a sort of a cosmos eye view of this occultation. So here's my station in Toronto, and here's the predicted path. I can see the same kind of information I saw in Occult Watcher here. I've got lots more information here about the details of this and different information about the path and everything here. So I'm able to put that whole package together and find out a lot more about this particular event. The other thing that's really cool here is I've got Finder chart, so I can have a look and preview what this star is going to look like. So I can see, oh, look, there's a couple of really bright stars and 3 bright stars in a row just outside here. So finding this should be a snap if I wanted to find this occultation. So it's going to occultate that star. So I got to find 3 stars in a row, little hockey stick thing here, and it's going to be hanging off there. So all of that information is online, and it's freely available to us all. All right. So I'm just going to stick here because that will make it better. So we talked a bit about Occult Watcher now, OW Cloud, I should say, and what it. In order to observe it with the latest technology, you need a telescope. It can be as little as 90 or 80 millimeters. It doesn't matter, as long it just controls how deep you can go and what events you would be able to get at. There are analog camera systems, a little old school, but they work just fine. IOTA, an organization I'll talk about in a minute, they're offering them for about $425 US. And there are also GPS-enabled cameras that do that timestamp, excuse me, I was talking about earlier, available from specialists. And then the newest and coolest is an integrated system called Astrid, which is using Raspberry Pi. So just for the benefit of the audience, I'm holding up the Astrid camera here. And this is an incomplete system, which is designed to work with any telescope, especially a computer-driven telescope. So at the front end here, we have the eyepiece. So you put this is the end you put in the telescope. And then it has its own Wi-Fi network. It does plate solving, so it will take you to the correct location. So you load in your occultation event, the one that you want to go see. And if you've got a go-to telescope, it will take you there. If you don't have a go-to telescope, it will take pictures of where you're looking, plate solve it for you, and tell you whether you should move your telescope this way or that way to get on target. And it will let you know the target that's there. It does the video recording for you, manual or automatic. So you can essentially watch it and keep an eye on it and do the recording by yourself. or you can set it to go overnight. So you can say, start at 2:38 in the morning and finish at 2:42 in the morning, and let me know how it turns out when I wake up in the morning, which is a really, really great feature. Um, you're able to import the data to this camera from Occult Watcher, so that all of the details that you need are already available, and that's really, really key. So I'll just show you a quick glimpse of what it looks like when you're driving your telescope, and then I'm just going to switch here from my current Wi-Fi connection to the Astrid camera. So I'm switching my Wi-Fi because it's broadcasting its own Wi-Fi on its own network. And so I switch over to that camera. And then I'm using free remote PC software called um, Real VNC. I have this set up here, and it says no such host is known. Oh, come on, you surely know. Yes, you know that host. So I can see it's broadcasting, so it connects. And here is the desktop. So I'm running a whole little PC on Raspberry Pi here, and the Astrid app is right there, and I can pull it up. Now, it's all in red night mode here, but you can see that I have occultations, and the key thing here is to get all 4 of these boxes in green, which means that you've got everything ready and set for your event. So the first thing is your site information. So the GPS needs to be connected and know where you are and download the exact location of where you're at. The GPS needs to be running and recording the time so that it can date stamp it on the camera. And once all of those things are in place, then you are ready to start observing. And you can set up various things here. There's a feature called exposure analysis, which will tell you, are you going to be able to see the target star, and allow you to adjust your gain and other video parameters to make sure that you can see it. You can control your mount, you can park your mount, and you're able to do the video recording and everything. So essentially, it's taking care of everything. It's driving your mount, it's taking care of the video recording, it's got a sensitive camera built in, 12 volts. It's impossible now to make a mistake when you are observing an occultation, unless, of course, you get the date wrong and you set it up to record an occultation one day after it happened. That is still, thus it is still possible to screw up an occultation, even with the best possible technique and technology that is available today. And I am proof that it is possible. So the only comment I'll have on it is that it's a Linux application. You can see here it's kind of a little. He's done a lot of work, and it's just coming to us from a fellow named Mark Simpson out of the Calgary Center, RESC Calgary. So he's done a great job here of trying to put this together in a way that is simple. It's designed to run on tablets or phones, so you can actually drive this from a tablet or a phone. You don't actually need a computer. But it is a little finicky, and you got to be kind of comfortable with the fact that you're running Linux here, and it will work well for most practical purposes as long as you follow the instructions. And it's kind of like every piece of astronomical equipment I've ever seen in that way. So getting back finally to the end of the presentation. So occultations have come a long, long way. Since we first began. I think the first occultation was confirmed in 1623, and that was an occultation of Spica by the moon. And so we have been doing a lot more in this area since IOTA became an organization back in 1975, and it's been continuing to grow over time, and it continues to be an interesting and exciting part of the hobby. And certainly, if any of you have any questions or would like to talk to me after the presentation, I'd be happy to review that. I would also encourage anybody who's interested to get involved. Occultations.org is the website of the International Occultation Timing Association, or IOTA. And also bookmark that website, cloud.occultations.net. put in your parameters and put in your coordinates and see if you've got anything coming up. Like I say, even if you don't want to get into the business of recording an occultation, wouldn't it be cool to see a star disappear for 4.3 seconds, just exactly when it's supposed to? And get more involved if you're interested. We'd love to help you out. And I know there are other folks in the club that would love to help you out with this as well. And that's it for me. Thank you very much.
Thank you very much, Dennis. I'm going to start off by asking my own personal question.
Sure.
Astrid is, I assume, as any good piece of astronomy equipment, is supposed to be almost waterproof because the amount of dew you will end up with at about in the early morning hours in September in this part of the world.
I don't know that answer for sure. It would be a good question to ask on the forum. I would probably put a plastic bag around it.
Okay.
But it has ventilation, and I think they're more worried about keeping the chip cool than they are about keeping moisture out. Okay. But the camera compartment is well sealed.
And how well does she handle in January at minus 25?
I can't answer that, but we'll find out, I suppose.
Any other questions from the room?
Yeah, I've got to ask, how much is an Astrid camera?
It was about $700 US.
Okay.
And Mark has a video online where he's actually he has put together a contraption to assemble the circuit boards himself, which I was very, very impressed by.
Okay, and does it have a built-in GPS, or are you slurping it in from your phone?
No, built-in GPS. The GPS antenna goes right there, and like I say, it complains if it doesn't find your GPS. And this GPS actually, when I tested it, I got a perfect GPS signal in 2 seconds, unlike my other GPS camera, which is much more finicky. So,
cool. Thanks.
Yeah.
All right. And no one else. Any questions online?
Yes. This is a question from Zapfan from Sweden. He asked, have you watched any Kuiper belt objects?
Well, one of the things that I think I have not personally, is to answer the question directly, but I think one of the applications for this, of course, is Kuiper belt objects are generally not well known. We classified as trans-Neptunian objects, TNOs. So those occultations will be very low probability. The shadow may or may not hit the Earth, and we don't even know exactly where on Earth it'll hit. But if you can nail it down and constrain that object, you would get it to work. And it should also be a relatively very slow occultation. So it should take 10 or 20 or 30 seconds because those objects are moving very slowly. So that's one of the reasons why there was a real push on to get more information from occultations for the Pluto probe, which was called New Horizons. And so this was actually one of the things they did, was they actually looked for an occultation which went across South America to constrain the location of the target asteroid for New Horizons. And that was part of their planning. Before they were able to actually see the asteroid, they were able to determine exactly where it was and refine its orbit through occultations.
Okay, Dennis, once
again.
One more question here. Thank you very much for a nice presentation. Just wanted to ask you maybe a stupid question, that meteor shower can cause occultation?
A meteor shower would, I suppose, in a very instantaneous sense, yeah, you could have a meteor on its way to Earth, like before it hit the atmosphere, could blink in front of a star, but you'd be hard pressed to tell that event from a high flying bird, which could also blink out a star as well, or even like an aircraft that's not, got its lights on or whatever. So yeah, it could, but it would be Yeah, but that's not, of course, what we're really interested in, but it's possible, I guess. Yeah.
Although on that note, there have been some rather famous astrophotos in which a shooting star happens to pass through while someone is taking the photo.
Yeah. Photo bombing by meteor debris. Yes.
All right, Dennis, thank you once again.
Okay.
And
thank you.
we're going to go back to fun facts while we set up for our last presentation of the evening.